All right. Hi, everyone. I'm going to go through the diversity of carbon with you and then also talk about functional groups and then cover two types of reactions that are going to be very common in our processes that we see throughout our time together. So, carbon is awesome, much like water. It has several characteristics to it that make it really fantastic for life. Carbon is special because it has its own branch of chemistry that surrounds it, organic chemistry. So we're focused on the properties of carbon and how it links up with other atoms and all the different um, functions that it'll eventually lead to. So some main details, anything that is organic means that it contains carbon. It can also contain hydrogen, but we're focused on the carbon for us. Carbon links up with many other atoms because of its bonding patterns. So it leads to some important complex molecules, and that's all surrounded by these atoms down here known as the chomps, right? Like chomp, but with an N for nitrogen. So those are all going to be identified in some later slides. And then carbon also will lead to some simplistic molecules, right, like carbon dioxide, but it will also lead to large macromolecules like proteins and lipids and carbohydrates and nucleic acids. So here we go. The first thing about carbon that we love is the fact that it has tetravalence, or that means that it can bond with up to 4 other partners, right? Its valence electrons are 4, therefore it has 4 open spots for some other buddies to come and join in. So that's tetravalence, tetra for 4. And it's going to be most commonly partnered up with hydrogen, oxygen, and nitrogen. There we go. My little pointer is back. All right, so that's tetravalence, which we should be comfortable with. Carbon is also super diverse because it can go through a single, double, or triple bond with its neighboring atoms. So we can see some examples here of how we have our single bonds over here with ethane. A change in the double bond in the center of our carbon backbone means ethene, and then ethyne is our triple bond. Again, carbon is amazing because of the potential large macromolecules it can form. Again, I talked about this earlier, carbs and lipids. We'll look into those tomorrow. And then in 2 days after that, we'll look at proteins and nucleic acids. But those are major players in the structure of all of life. And we want to know how carbon can impact that and what properties it brings each of those. So beyond its single, double, and triple bonds and the fact that it has its tetravalence, it can be found in different shapes. So it can be in a long, lengthy chain, it can be in a ring shape, or it can have some branching patterns to that. So again, we can see some different examples of that here where they're in chains, with the double bonds being in different locations, still in kind of that chain. Branching, meaning, right, we can start to see different points where it links off with our carbon backbone and then our rings, and the differences between maybe a single or double bonded ring for carbon. I'll move myself here. Carbon also has the ability to to show isomers. And so an isomer is going to represent a molecule that has the same molecular formula, but different atom arrangement or different overall function. So molecular formula are our atoms and the number of each of those atoms in there, right? So H2O would be our molecular formula, and then the atom arrangement would be like, the bent shape that it has. So isomers might have they will have the same formula, but their shape is going to look different. So I have the 3 linked below here, so we can see that. When they have the same formula but different arrangement, structure determines function in biology. Key component that we look at. So if it has a different structure, that means we're going to see different properties and results, resulting functions. The first one over here is our structural isomer. So we're looking at pentane and methylbutane. They both have a 5-carbon backbone, and I think there's 17 maybe hydrogens all around them. Anyway, same molecular formula, but their structure is completely different, right? We can see that there's a chain versus a branch, and I'll get that thing out of the way in a moment, right? So if they have different structures, their functions are different. Our cis versus trans isomers deal with the general spatial arrangement. So you can see the examples down there. They both have the carbon backbone. They both have 2 hydrogens, and then there's going to be something else attached to them. But where those something else's are attached is different, right? So we have the angles over here, which is why I didn't want to use my mouse, versus being both linked at the top. Again, having those 2 different shapes, it's like trying to pat your head and rub your belly at the same time. That leads to a different function. Okay, and then our last one, known as enantiomers, is an example of an isomer where, right, we have our structure, but it's just a mirrored image, right, of each other. So we have this same molecular formula in both cases for our L and D isomer down there, but the way they actually arrange gets flipped and mirrored. So I like to talk about thalidomide. I'll attach the link that goes along with this so you have an idea of what an enantiomer looks like, right? It seems relatively like simplistic, right? They're mirror images of each other, but this is pretty intense on the effects that they can have on the overall properties and functions of them. So, for example, thalidomide was a drug that was utilized to help reduce morning sickness for our pregnant women out there, which was great. And so that drug came out, and then people tried to replicate it. They knew the molecular formula. They knew how to, you know, generally copy that and make it distributed at an easier rate, as well as maybe lower some costs. But people took some side steps and didn't really look into the chemistry behind it, and they ended up creating, you know, an enantiomer of it or a mirror image of it. It looked the same molecularly to them, but they didn't think about the overall functions or properties that this thalidomide ended up having on the mother and the children. So eventually, the bad version or the mirrored image of it led to some severe birth defects and also had some really adverse effects on the body. And now we realize that this thalidomide has some actual benefits and can be used to help treat things like cancers and things like that. But initially, there was no, I don't know, research out there that led to the understanding of these enantiomers and how dangerous they are. So I'll link that in there because it's actually interesting to hear about if you haven't heard of thalidomide before. Another example here for you um, on our engineering pharmacy connection would be ibuprofen, which it's intended to assist with pain and inflammation. And then if you have it's an enantiomer, there's one that does not really help at all with that. And the same thing with albuterol, holler for asthma, um, a helpful one, and then one that is hindering. So you can look into those if you are interested. Our next category are going to be functional groups. So we'll be able to identify molecules with their carbon chains or their backbones, and then there are going to be specific molecular formulas that come off of our carbon that are going to be repeating. and they have some specific properties to them, like polar versus nonpolar, or acids versus bases. And we want to know these 7 functional groups. So let's get rolling. I will give you a graphic organizer to help you through this, or you can take your notes however you want on that, or you probably already have. So we're going to work through identifying these over and over again. Hopefully you remember seeing hydroxyls. These are super easy to identify because it's HO or OH. You'll be able to identify that in your chemical formula. And the compound names mean alcohol, so that's relatively easy to connect with, right? So if you're looking at a diagram or a molecular structure here, you can clearly see OH is one of our molecules off to the side, so that is a hydroxyl group. Carbonyl is our second group. That's when we have a carbon double bonded to an oxygen. And those lead to our ketones. So sometimes you see this group being referred to as the ketone group instead of carbonyl, but I am going to reference it as carbonyl all the time. Again, carbon double bonded to oxygen. There's one, and over here on our propanol is another carbonyl functional group. Carboxyl is our next one. So carboxyl is also referenced as carboxylic acid. But this is COOH. So you're going to look for, most commonly, a carbon double bonded to an oxygen, which looks like carbonyl, but hey, there's a hydroxyl as well. So it's the combination of them all next to each other. I hate that my mouse is lagging right now. But the combination of them all together right here makes a carboxyl group. So we can see that linked to the end. So double check and say, hey, do I just have carbonyl, or is there a hydroxyl attached as well? Carboxyl groups are found in amino acids. So that's a good one to look for. Amino group, also found in amino acids, hence its name, or amines, you might see that. They're also found in our nucleic acids. So you're going to see nitrogen in our amino group, and that's NH2. So you can see that one there, over here. And this is an ionized form of NH2, right? So we can see the plus symbol there, and that's also another example of that. So that's our amines. Sulfhydryl gives away its name, which I love this one because it's so easy to find, hence sulf and hydrogen, so SH, and they might be referenced as ethyls, SH. And then our phosphate group, again, easy to identify because they're going to have the P for phosphate, and oxygens are surrounding it. So phosphates are going to be found in our lovely nucleic acids. So PO4, or the ionized form of phosphate, looks like that, PO4. And our last one is methyl, which is a carbon with 3 lovely hydrogens attached to it. So CH3 is the hint for that, and you can see that here. We'll do lots of practice with this later on. All right, and our last piece is talking about the very important chemical reactions that happen in biology. So how do we start with something simple with our building blocks and end up something with something more complex like our macromolecules? They're going to go through some type of reaction which allows these monomers, or these building blocks, or simple, small organic molecules, to link together to create something larger, known as a polymer in our case. Poly meaning many, mono meaning single. So that's how we relate those together. Anyway, when monomers link together, they're going to be linked together with covalent bonds. We might see some peptide bonds in there, and allow that to shape a large macromolecule, right? Macromolecule. So examples, we've talked about our process of the central dogma, how we go from DNA to RNA and end up with a protein. Protein is our macromolecule. I'm going to kind of work backwards here. And its monomer is known as an amino acid, which I referenced earlier with that amine functional group. So multiple amino acids will link up together using a peptide bond. Those amino acids are the monomers. The peptide bond allows them to link together and create a polymer known as a polypeptide. And then that polypeptide will eventually fold into something known as a protein. So we're starting with something small that will lead to something larger, and that larger should really be over here. Sorry about that error. All right, so our two main reactions that we see in biology are going to be dehydration synthesis versus hydrolysis. Let's break those words down and it'll make our lives so much easier. Dehydration. What does it mean when you're dehydrated? It means that you had some water loss. So that's exactly what happens here. Synthesis is to make. So we are going to see two monomers combining to make a polymer by means of removal of water, dehydration synthesis. So you can see that here. Again, we're making polymers, taking two monomers, removing a water to make something large. Okay, and then hydrolysis, hydro we talked about, water. Lysis means to split. So you are going to break something down using the addition of water in hydrolysis reactions. So if you can identify where water is in your reaction as a reactant or a product, you'll know whether or not you have dehydration synthesis or hydrolysis going on. So they are mirrored reactions of each other. So some examples of that, again, we've got a dehydration reaction here where we can see one small polymer over here on the left is going to link to a monomer over here on the right. And we can see in between here, one has a hydrogen, this one has a hydroxyl. That's where our bond is going to happen. So water is out, dehydration is happening, and then they can link together and make a long polymer. And down below is the reversal of that, where we have our long chain happening. Water comes in and busts up that molecule or our polymer and breaks it down, and then we can see where that water went to in the end and split its forms. So another look at it. You can't have too many examples, can you? If you get it, you got it, you're good. With our examples of some amino acids here. So we have glycine. We can see where that water is being highlighted between our two amino acids, glycine and alanine. That water is out, dehydrating it, linking it up with our peptide bond because those are amino acids through dehydration synthesis. All right, I am going to stop there and we will hit the macromolecules in our next lesson.